Fiber optic cables play a crucial role in our daily lives, connecting us to the internet and allowing us to enjoy services like video streaming, online gaming, and much more. These cables form the backbone of our global communication network, allowing information to be transmitted almost instantly around the world. To understand how fiber optics work, we first need to review some basic optics concepts. You have probably heard that the speed of light in a vacuum is approximately 300,000 kilometers per second. Every time this fact is mentioned, it is clarified that it is in a vacuum because light travels at other speeds when it passes through other media, such as air, water, or glass. The ratio between the speed of light in a vacuum and the speed in the new medium is what is known as the refractive index, and it is an intrinsic characteristic of each material. But the change in speed is not the only thing that occurs. When a light beam passes between two materials of different refractive indices, its path is also affected, similar to what happens when we try to see something in water. When the angle of incidence is small, the light beam undergoes a slight deflection as it passes from one material to the other, a phenomenon known as refraction. However, when a critical angle is reached, the change in path is so great that the light can no longer pass through the other material. When this occurs, the light, instead of being refracted, is completely reflected back to the original material in a phenomenon known as total internal reflection. This process occurs when light passes from a medium with a higher refractive index to one with a lower index. In other words, the interface between the two materials will behave as if it were a mirror, this being the fundamental principle of fiber optic cables. Understanding this, fiber optic cables are composed of three main layers: the core, the cladding, and the protective sheath. The core is a thin, transparent filament made of glass or plastic. Surrounding the core is the cladding, which is also made of glass or plastic, but with a different refractive index than the core. And finally, the protective sheath, an outer layer that protects fiber optic cables from physical and environmental damage, can be made of materials such as plastic, Kevlar, or steel. In this way, when a beam of light enters the core, it will be reflected every time it reaches the edge with the cladding, being guided along the cable for long distances. There are two main types of fiber optic cables: single-mode fibers and multi-mode fibers. These differ in the size of their core and how they transmit light signals. Single-mode fibers have a smaller core, usually around 9 micrometers in diameter. This allows light to travel in a single straight path with minimal signal loss, making them ideal for long-distance transmission. Multi-mode fibers, on the other hand, have a larger core, usually around 50 to 60 micrometers in diameter. This allows them to transmit multiple light signals simultaneously, each taking a slightly different path. While this allows for higher data transfer rates, it can also cause signal degradation over longer distances due to the different travel paths. As a result, multi-mode fibers are better suited for short-range applications such as local area networks and data centers. The process begins by converting digital data, such as text, images, or video, into binary light signals using devices such as LEDs or lasers. LEDs are cheaper and are used in short-range applications such as local area networks, while lasers, given their more coherent and powerful light beam, are ideal for long distances and higher speeds, such as in submarine cables or backbone networks. These light signals are sent to the fiber optic cable, where they travel through the core by bouncing off the cladding through total internal reflection. In addition, to increase data transfer rates, a technique called multiplexing is often used, specifically wavelength division multiplexing, which combines multiple light signals at different wavelengths within a single fiber. Once the light signals reach their destination, they are converted back into electrical signals by a receiver or demultiplexer. The latter receives the combined light signal, separates them again, and sends them to the appropriate device or network. Additionally, it should be noted that there are two main types of fiber optic-based networks: passive networks and active networks. In active networks, electronic devices such as amplifiers or repeaters are used along the cable to reinforce the signal. While on the other hand, passive networks do not require these devices. making them more energy efficient and less expensive. However, they have a limited range compared to active networks. Fiber optic cables have several key advantages over traditional copper cables, making them the preferred choice for modern communication networks. First, they offer higher bandwidth and data transfer rates, allowing for faster internet speeds and more efficient communications. Second, they are immune to electromagnetic interference, ensuring a more reliable and stable connection. Third, fiber optic cables experience lower attenuation and signal loss compared to copper cables, allowing for efficient data transmission over long distances. Additionally, fiber optic cables are thinner and lighter than copper cables, making them easier to install and reducing infrastructure costs. And lastly, since fiber optic cables do not emit electrical signals, they are less susceptible to eavesdropping and interceptions, improving communication security. In short, fiber optic cables have revolutionized the way we communicate, enabling faster, more reliable, and more secure connections in a wide range of applications and fields. That's all for now, and see you in the next chapter.